Welcome back, Patriots. This is Mr. Love, aka the Math Patriot, bringing you another fun and exciting lesson in the world of high school geometry. I apologize up front for not having all my fancy stuff up today. We're going to have to do this the raw, basic way. My recording situation is just a little bit different today. Let's just go ahead and get this over with as soon as we can. You should have the notes thing up the note sheet up that I put onto Google Classroom. And we got 10 examples to do today. I cleared out some of the riffraff, and I'll kind of make a note of that whenever we get there. The things on your note paper are a little bit different than the notes that we have here, just order-wise, but I trust you guys can figure out exactly where we are. Last class period, we covered area of a whole bunch of shapes. Today, we're going to focus solely on circles and sections of circles. So we'll talk about what sectors are. Oh, we've already talked about sectors, actually, but we'll just go ahead and recover it when we need to. All right, first off, area of a circle. So you've seen this formula before, pi r squared. Please be very, very careful not to get that mixed up with your circumference formula, which is 2 pi r. You got to use those in the appropriate context. Important thing is that since this is the radius squared, let's say that this is 4 millimeters for the radius. Whenever I plug that in and get area equals pi times 4 millimeters squared, that's going to end up giving me 16 pi millimeters squared. The important thing here is that that unit is a squared unit, which indicates area. You'll notice that over here in our circumference formula, there is nothing that multiplies units by its, or like meters times meters. So you're going to get just a regular old meters at the end of that. This one, you would get circumference equals 2 times pi times 4 meters, which means that I've got 2 times 4 is 8 pi, and then the meters is left alone, meaning that this guy right here is a distance unit as opposed to an area unit. So please, my point there, make sure that you are using the correct formula for the correct application. Let's go ahead and jump into examples, if I could control my scrolling. All right. Find the area of circle P. So area is pi r squared, which means that area is pi times 12 meters squared. And then whenever we go ahead and multiply that through, that gives me area equals 12 times 12 is 144 times pi meters squared. Now we're going to have to be careful with directions here. The reason is that if we say round or nearest hundredth or whatever, then we're going to jump over into our handy dandy calculator over here and type it in. If not, we are going to assume, the assumption here is that we want exact, which means no rounding. No rounding. No rounding. Now, the way you accomplish that is just by leaving it in terms of pi. 144 pi meters squared is much more accurate than rounding that thing off to 2 decimals because we're not doing any rounding at all. Okay. Example 2, a swimming pool company manufactures circular covers for above ground pools. If the cover is 1 foot longer than the pool on each side, find the area of the cover. So, notice here that we've got 2 circles that are concentric, meaning they have the exact same center. I'm going to do 2 areas and then subtract them out, because what I'm actually looking for here is the area of, hold on, I take that back. We don't want the area of the concentric circle. We want the area of the entire thing, because the pool is going to cover the entire thing. The reason I say that, this used to be a trampoline problem, and I was using this as a massive trampoline, and we were finding the area of this little guy, and I decided to go ahead and change that out. Sorry for that. So what we're going to do is find the area of the entire thing, which means area formula is pi r squared. I need to find the radius of this circle. So for my small inner circle, if the diameter is 18, the radius is 9 feet. Then I'm going to look at the entire thing, this entire distance. Radius is going to be the 9 foot plus 1 foot is going to be 10 feet. Now we jump over and plug that in. Area equals pi times 10 feet squared. And then 10 times 10 is 100 pi feet squared. And it doesn't ask us to round, so we're going to leave that alone as 100 pi feet squared. Number 3, find the diameter of a circle whose area is 153.9 square centimeters. Here we go. Round to the nearest hundredth. So this one we are going to be using our calculator and just rounding off. So find the diameter of a circle whose area is 153.9 square centimeters. Okay. I use my formula, pi r squared. Then I'm going to plug in what I know, which is my area, 153.9 centimeters squared equals pi r squared. Now, we are trying to solve for r here. So we've got to unravel this thing one piece at a time. Now, the first thing I'm going to do is divide by pi on both sides. Then I'm going to take the, well, you know what? No, I'm going to do it this way. What that gives me whenever I'm done with that is 153.9 centimeters squared over pi is equal to r squared. Now I'm going to take the square root of both sides. The reason is that's going to get rid of my square here. So whenever I take the square root of r squared, that leaves me with r. Whenever I take the square root of, I'm doing this a little bit backwards, but when I do the square root of centimeters squared, that's going to give me centimeters. Then the rest of this I can type into the calculator. If the calculator will turn on. There we go. Square root of 153.9 divided by pi. Ooh, no. Make sure that divided by pi is underneath the square root and you'll be fine. So what that tells me is that my radius here is equal to 6.999. Now we're around the nearest hundredth, so that's just going to round up to 7.00 centimeters. Now also be careful here because it's asking us to find the diameter. So if the radius is 7 centimeters, then the diameter is 14 centimeters. All right, moving on. Sections of circles. Okay, now the sector of a circle is a region bounded by a central angle and its intercepted arc. I believe you got a few things to fill in the blank there. All that means is we've got a central angle, which is here angle A, and the intercepted arc, and it's everything there in the middle. That is a sector. Now, a segment is a region bounded by an arc and its chord. So I've got this arc and the chord that intercepts, and then that is called the segment. Notice what's actually going on here is that we've got an intercept or a central angle, and this is actually one of the things I decided to cut out. We're not going to be actually calculating the areas of segments. The way you would do it is by calculating the area of the sector and then subtracting out this area of the triangle right here. But I just decided with this distance learning thing going on, it would be a little bit too much for me to throw at you guys, and it's not going to be used hardly anywhere else in your math progression anyway. So I went ahead and threw that out. So you're not going to have any of those, but I do want you to know what this segment of a circle actually is. Okay, area of a sector is just x over 360, where x is the central angle, times the area, pi r squared. Now, think about what we had when we had arc length. Length was x over 360 times 2 pi r. Now, we simplified that to say that it was x over 180 times pi times r, and the reason was that this 2 and this 360 simplified to become this 1 over 180, or x over 180. But it's essentially the exact same idea. In both cases, all that this represents, the x over 360, is the percentage of the circle that this represents, that the sector represents. So basically, if x is 90 degrees, then this is 1/4 of the circle. Well, notice that 90 divided by 360 is 0.25, or 25%. And we're taking that 25% and multiplying that by the area. So that's all that we're doing there, is we're coming up with the percentage of the circle and then multiplying that by the entire area. And that concept will become important later on when we do some of these other pieces, or do some of these examples later on, because it will allow us to shortcut the process if we understand that all we're doing is talking about a percentage. And I'll bring that up when we actually get there. Okay, find the area of the shaded sector and then find around to the nearest hundredth. All right, so we got area equals x over 360. X is the angle measure, which is 36 divided by 360 times pi times the radius, which is 5 inches squared. Now, since this one asks me to round to the nearest hundredth, I can literally go to the calculator and type this in exactly as I see it. 36 divided by 360 times pi times 5 squared, which gives me that my area, let's use a pen instead of a highlighter, area equals 7.85 inches squared. Now, to drive home a point here, here's what I want to go do. I want to find the area of the entire circle. Okay, so I'm going to highlight this whole thing. Highlight this whole thing in orange. Area of the whole circle is just pi r squared. So that's pi times 5 squared, which is 25 pi. And then 25 pi is 78.54 inches squared. Okay, now that we've done that, I want you to think about this particular angle right here. 36 degrees divided by 360 degrees is equal to 10%, 0.10. Now look at these two numbers. The area is 78.54. The area of the whole circle is 78.54. The area of the circle is exactly 1/10 of that, exactly 10%. Just divide 78.5 by 10, you do get 7.85. That's my point. This is just nothing more than a piece of the pie, literally a piece of the pie, and we're just multiplying it by the area. I'm sorry, by the percentage. Okay. Number 5 is one where we're able to shortcut it if we understand what's going on here. Okay, so we've got our formula here. We got a pi slice that we're doing here. It's x over 360 times pi r squared. Okay, and we know that our diameter is 9 inches. Therefore, our radius is 4.5 inches, and it's cut into 10 congruent slices. Now, if it's 10 congruent slices, now one approach to this would be to draw our circle and then figure out what is our x value here, and plug that in. Or we could understand that essentially, since this is a percentage, all we're doing is just saying that it's 1 out of 10 times pi times r squared. Now, when you think about that, that's exactly what you would have done over here. If you'd done that, that would be 360 divided by 10, which is 36 degrees. You'd plug in 36 divided by 360 and get 1/10. So my point is, it's a similar thing. If you want to go that route, by all means, go ahead. But if it's 10 congruent slices, then we're looking for 1 out of 10. Now let's just plug that in. Area equals 1/10 times pi times 4.5 inches squared. We also want nearest hundredth, so we can jump to the calculator. 1 divided by 10 times pi times 4.5 squared. So that area equals 6.36 inches squared. There we go. Oh, I want to go ahead and point this out on here. Some students get confused when they're looking at this particular setup right here because they're thinking that it's actually 1 divided by 10 pi, as in the pi is in the denominator here. I want to go ahead and prove a point. If I decided to do this whole alpha y equals, I hate this view, by the way. I'm just showing it to you to prove a point here. 1 divided by 10 times pi times 4.5 squared. Notice we get the exact same answer. The reason is that whenever this guy, the calculator, reads this, it reads order of operations whether you want it to or not. And so anytime there's nothing written in between there, it just assumes it's a multiplication sign. So it's 1 divided by 10 times pi, and there's no groupings there. There's no groupings around the 10 and the pi, no parentheses. And so it understands that pi is in the numerator. Okay, so be careful with your calculator. If you need to, jump over to that other view. It doesn't matter to me. Personally, I think that's better for you to get used to seeing it the top way, but whatever. As long as you can get the right answers, that's what matters here. Okay, find the area of the shaded sector. You know what? I'm going to skip this one. I don't know why I use this 36 degrees so much. It's the same process over and over again. You get the idea. Move on. Okay, our next few examples, I believe all the rest of these, yes, are composite figures where we're having to do the area of multiple shapes and add or subtract as necessary. So we're going to be trying to find the area of the shaded sector on all of them, and this one, yes, we're going to be rounding to the nearest tenth. So we've got two things we've got to do here. We first need to find the area of the rectangle. Then we need to find the area of the circles and then subtract those out from the area of the rectangle. So what's actually going on here, our total area is equal to the area of the rectangle minus the area of the circles. Now I'm putting that AC. I guess I should probably put minus AC because you got two different circles, so circle 1 and circle 2. But I also want to point out here that when I look at these, I notice that this diameter going across is the exact same as this diameter going across. So these two circles are going to have the exact same area. So area of circle 1 and area of circle 2 are going to be equal. Now let's go ahead and find those since we're talking about them. Area equals pi r squared. Now we got to figure out what the radius is. Now I know that each of these, since I've got a rectangle on the outside, each of these two diameters is going to be equal to 5 centimeters. So D equals 5 centimeters. Therefore, my radius is half of that, which is 2.5 centimeters. So area equals pi times 2.5 centimeters squared. So let's see, 2.5 squared. I don't know why I'm typing that at 6.25. 6.25 pi centimeters squared. I know it says round, but I always want to round on the very last step. So I'll do that at the end. Now let's also go in and find the area of my rectangle. So area of a rectangle as a parallelogram is base times height. And we can see my base here is 10 centimeters times my height, which is 5 centimeters. So my area is just 50 centimeters squared. All right, now let's plug this in. Okay. Area of the rectangle. Oh, I don't know why I did that. I should have actually written it down, which is 50 centimeters squared minus 6.25 centimeters squared minus 6.25 centimeters squared. So we're just going to type in 50. Oh, I made a mistake. Let me back up a little bit. 6.25 pi centimeters squared. 50 minus 6.25. 50 minus 6.25 pi minus 6.25 pi. Therefore, my area is 10th would be 10.7 centimeters squared. And yes, I realize there are some more efficient ways I could have written that down or typed it in. I'm just going for short and sweet right here. Okay. Example 8. Find the area of the shaded sector here. Now, when we look at our composite, what I'm going to have to do is find the area, that's circumference, area of the circle, and then subtract out the area of the triangle. So let's go ahead and find the area of our circle first. Actually, you know what? In order to do that, I got to figure out what my diameter and everything is. Looks like I've got an isosceles triangle here, and since this angle intercepts this inscribed angle intercepts the ends of a diameter, then I know that this is going to be a right angle, one of the lessons we learned back in our circle unit, which means I've got a right triangle. It's a right triangle that is a 45, 45, 90 because I know that these two are equal. Right isosceles is 45, 45, 90. So on my 45, 45, 90, it was S root 2. So whatever's on the leg, I multiply by root 2. So my diameter, this guy being my diameter, is just going to be S root 2, where S is 5 root 2. So that equals 5 root 2 times root 2. By the way, this 5 root 2 got plugged in here for the S, which is where that 5 root 2 came from. This root 2 is that root 2. So now 5 root 2 times root 2, well, root 2 times root 2 is root 4, which is 2. This guy comes out to 10. If you don't believe me, you can type it into the calculator and you'll get the same thing. So that is 10. Now, if my diameter equals 10, then my radius is 5. So area of the circle, being pi r squared, is going to be pi times 5 meters squared. 5 squared is 25 meters squared. Great. Now let's do the area of our triangle. Since it's a right triangle, I can use this as my base, and this is my height. When I plug it in to the area formula, 1/2 base times height, 1/2 times 5 root 2 times 5 root 2. Now, 5 times 5 is 25, and then 5 times 5 became 25, and then root 2 times root 2 is root 4. 1/2 times 25 times square root of 4 is 2. And then this 1/2 and this 2 are going to cancel each other out, meaning that the area here is just 25. Now I got a problem, because I said that that was 25 on both. Oh, you know what my mistake is? It was right here. This pi didn't make it here. So let me go ahead and put that in there. It is 25 pi meters squared. I apologize for that. So this is the area of my circle. This is the area of my triangle. Let's go ahead and plug that in now. Area of the circle is 25 pi meters squared minus area of the triangle is 25 meters squared. And now we can go to our calculator. turn on. 25 pi minus 25. And my area is 53.5 meters squared. Two more examples. Find the area of the shaded sector. Now, this one at first starts to look like it's more complicated than it really is. I am going to approach this thing as if basically try and collect all of the circle piece or all the shaded sectors together. Okay, so basically you can't see that, I'm doing it in yellow. All of these I'm going to put together as one massive section like this, and then each of the three pieces there I'm going to stick together in there. The reason I'm doing that is basically just kind of sliding those pieces around. Basically think of an actual pie. You know, if people took these three slices out, where the 45 is, you could just slide those three all together and it wouldn't affect the area of the top of the pie. So the reason I'm doing that is because it'll make it easier for me at the very end of all this. So I'm going to notice also that all three of these arcs are congruent, meaning that they're all going to have the exact same central angle. So each of those is equal to 45 degrees. So whenever I slide and collect all of them over, this x here is just going to be 45 times 3, because I've got 3 of those white wedges that all need to be accounted for. Now, 45 times 3 is just 135. So x equals 100. 135. Now, to find my shaded area over here, I want to know the measure of this arc, which is just going to be, I'm going to go ahead and call that y. 360 minus x, or 360 minus 135. My brain ain't working today. 225 degrees. So now for the area of my shaded portion, which I've marked in orange over there, it's going to be area equals, now normally that's an x, I'm going to throw a y in this because I'm talking about this shaded section over here. Oh, not equals, times pi r squared. So that looked like 2,250 equals 225 over 360 times pi times 2 inches squared, and nearest tenth, so I'm just going to type it in. 225 divided by 360 times pi times 2 squared gives me my area is 7.8. Ooh, 85 becomes 7.9 inches squared. All right, the last example of the day. I'll run it out right at 30 minutes, so we'll get this done as quick as we can. Find the area of the shaded sector. This guy looks kind of funky. Now we've got several different pieces going on here. The first thing I want to notice is that each of these, well, this whole thing overall is a semicircle. So the overall thing is going to be, area of the semicircle is going to be 1/2 pi r squared, because I don't have this bottom half of the circle here. So the semicircle is 1/2 pi r, need my r, squared. Now, I also want to notice that this piece that is missing, and this piece that are missing, and this piece that are added all have the exact same radius. And so what's going to happen is that these two are going to essentially cancel each other out, because what's happened is I've cut the area out, or this piece out, and just flipped it down and it's there. So these two are cancel each other out, so I don't have to worry with messing with those. But I do have to find the area of this piece. I'm going to highlight it in blue here. And that one is going to be subtracted out from the semicircle. Remember, technically I should have subtracted out this piece too, but since that one got added in, those are a wash. I don't have to worry about these two pieces. So it's going to be 1/2 pi r squared for the whole thing. And so then I'm going to subtract out 1/2. Let me figure out how to write this the right way. Okay, so I'm going to have the area of the whole thing is equal to the area of the large figure minus the area, and I'm just going to call that of that single hole. So this is the large, and here's your hole. All right, and they both have 1/2 pi r squared because they're both semicircles. So let's do the large area first. And I'm going to do that one in, you know what, let's do that with orange. So its area equals 1/2 times pi. It looks like my diameter is 12, therefore the radius is 6. And now 6 squared is 36. 36 times 1/2 is 18 pi. I guess I should make that inches squared. That's the large one. Now let's do the small one in blue. Now I got to figure out what the radius of this thing is, and forgive me, I'm going to erase all this now so I can figure it out. Well, the whole thing is 12, and each of these three has the same radius, which means that, oh, this is going to be the same, this is going to be the same, and this is going to be the same. So if I count those up, it looks like I've broken up this 12 into 1, 2, 3, 4, 5, 6 congruent pieces. So that means that for my small one, the radius is going to be 12 divided by 6, or 2 inches, because that thing is broken up into 6 congruent pieces. So area is, again, 1/2 pi r squared. So area equals 1/2 times pi times 2 inches squared. Now 2 squared is 4, times 1/2 is 2. 2 pi inches squared. Now jump up and do the whole thing. Area of the large figure, which is 18 pi inches squared, minus area of the small, which is 2 pi inches squared. I'm going to go ahead and point out that this one we could have rather easily come up with an exact, because 18 pi minus 2 pi is just 16 pi inches squared. But if we want to round it, let's go ahead and do that. Turn on calculator. 16 pi. So my area is 50.3 inches squared. And that's all I've got for you for today. I hope that was not too intense. Biggest piece of advice I can give you for all of the composite figures: figure out what the biggest shape is, figure out what you got to subtract out of it, and just keep track of those two areas separately, and then subtract them at the end. For sectors, all you want to do is know the measure of your central angle, and then it's x over 360 times pi r squared. However, you can always use that percentage of the circle if you need to. But like I said, that's it. As always, guys, stay safe, please stay healthy, and stay patriotic.